Could 3I/ATLAS be the key to a deeper theory of how wanderers from the galactic suburbs really behave? I think it's fair to say it's interesting. 3I is the shorthand astronomers use for the third confirmed interstellar object to drift through our celestial neighborhood. ATLAS names the survey that first flagged it, the Asteroid Terrestrial Impact Last Alert System. On the first day of July 2025, one of the ATLAS telescopes, this one in Chile, noticed a speck moving just wrongly enough that the usual bookkeeping wouldn't do. When the orbit was fitted, it wasn't an ellipse that closes on itself, but a hyperbola that never returns. That is the signature of a visitor from the wider Milky Way. NASA framed it simply: this is only the third time we've caught such an object in the act, after one I called Oumuamua and two I called Borisov. Now, a hand-wavy but honest definition, an interstellar object is a fragment of somewhere else, ice and dust or rock, ejected long ago by gravitational pinball in another planetary system, and then set adrift for millions or billions of years until chance brings it into the sun's domain. What sets 3I apart isn't only provenance, it's the way its path must be interstellar. The orbit is so strongly hyperbolic that no flyby of a planet here could have whipped it to such speed. Reuters put the broad facts plainly discovered on the 1st of July, approaching within the orbit of Mars in late October, moving tens of miles per second and no threat to Earth. That's the benefit: we can see these things while staying safely distant. History helps steady the hand. With one eye, Oumuamua, we glimpsed something puzzling: no obvious coma, odd acceleration. With two eye, Borisov, we saw a more familiar, gassy comet, but with intriguingly pristine ices. 3I arrives as a kind of synthesis. It behaves like a comet, an active nucleus wrapped in a coma. Yet even the ordinary has begun to look strange when measured with modern instruments. ESA's short primer puts it clearly: 3I/ATLAS is new, only the third of its kind, and therefore precious. We are building a lineage. Each object adds a rung to the ladder. Let's picture what you'd actually see through a modest telescope. Not a naked eye spectacle. This one is faint, comfortably fainter than the comets that make evening news. NASA's overview notes that it will never brighten much for backyard observers because of geometry. At closest approach to the sun, it is tucked near solar conjunction, from Earth's point of view practically behind the sun's glare. So our best looks may come from spacecraft and professional apertures. That limitation is not a disappointment, it's a clue. To learn anything beyond there, it is we will lean on spacecraft vantage points and big mirrors. Now to the conceptual tension, the bit that makes me sit forward. Several teams have reported a prominent jet, a stream of gas and dust apparently directed sunward. That sounds backwards. Tails normally point away from the sun, swept by solar radiation and the outflowing solar wind. But here's the dual perspective move. From our external vantage, if an active region on the nucleus happens to face the sun and grains launched at low speed fall under solar gravity, while sunlight pressure sorts them by size, you can create structures that in projection look sun-pointing. Live Science spoke to experts who emphasized this is not witchcraft, just comet physics in a difficult geometry. The beautiful lesson is that even normal behavior looks uncanny when you catch it in the right light. Another possibility, and I stress it as a possibility, is that 3I's activity will evolve as it rounds the sun. Anti-tail-like features can flip into a conventional tail as viewing geometry and dust grain sizes change. That's a reasonable hand-wavy picture, consistent with past comets and with some early modelling chatter. The key point is that we can test it because multiple observatories, including those orbiting other worlds, have the comet in view. If Mars orbiters or Jupiter spacecraft instruments sample the charged particles and dust environment, we might constrain grain sizes, outgassing rates, and even the rotation of the nucleus. Space.com noted the intriguing prospect that a NASA probe near Jupiter could be showered with comet-driven particles, offering a kind of in-situ taste of interstellar dust. That would be a rare gift. So let me build a simple mental model. Imagine a dark, tumbling body, perhaps a few hundred meters up to several kilometers across. We'll refine that, coated in ices that were laid down under a sky not our own. The sun's warmth awakens pockets of carbon dioxide and water ice. Gas jets drag dust free. Sunlight sorts the grains. Plasma from the solar wind threads through the cloud and bends it. And all of this plays out under a geometry that changes hour by hour as the object moves on a path it will never retrace. That's not hand-waving. That's the calculation we've done for many comets here at home, now applied to a sample from away. NASA's and ESA's briefs set the stage. Our task is to fill in the detail. But I think it's fair to say the deepest strangeness isn't the shape of a jet. It's the idea that we're starting to build a population of interstellar debris with different personalities. 1, I look like a shard. 2, I look like a textbook comet from a very cold pantry. 3, I seems to be active but geometrically tricky. That variation is the point. If we can measure composition ratios of water, carbon dioxide, perhaps carbon monoxide, and trace volatiles, and compare them to solar system comets, we begin to glimpse how planet-forming disks elsewhere cook their ices. If differences are small, that suggests a kind of chemical universality. If large, it suggests diversity born of different star types and disk histories. NASA's plain statement that 3I is unmistakably interstellar because its motion cannot be explained by any planetary sling here gives us permission to treat its chemistry as a message from another nursery. There's humility here too. We don't know the nucleus size yet with confidence. The coma hides the core, and our viewing angle is unhelpful. We don't know whether outgassing will ramp up or collapse as perihelion passes. We don't know whether we'll catch subtle non-gravitational accelerations, the tiny rocket effect of jets that might tell us something about the symmetry of activity across its surface. And that not knowing is not a failure, it's a research roadmap. Each uncertainty points to an observation. You can try to make a model, you can try to falsify a question you can put to the data. Put it this way, we are beginning to map not just a sky but a sample space. 3 interstellar objects is not many, but it is more than one. And with each fresh wanderer we can ask cleaner questions. Do the ices match ours? Do the dust grains respond to sunlight in familiar ways? Does the distribution of spin periods or shapes look like homegrown comets or not? Reuters' early reporting set the logistics. NASA and ESA have filled in the basics. Now we wait not passively but with telescopes, pointed algorithms, sharpened, and a healthy skepticism ready to meet surprise. So, if that's the hook and the handrail, what's the paradox? It's this 3I/A, TL. AS looks in one sense ordinary, a faint, outgassing comet too far for spectacle, and yet in another sense it refuses to be fully typical. From the outside you'd say just a small body with a jet. From the local frame, its own ancient chemistry, its long voyage, its geometry near the sun, the familiar becomes alien again. In the next part, I'd like to trace the history ladder from early predictions of interstellar comets to the detection pipelines that finally found them, and then ask how exactly we turn a fuzzy coma into numbers, production rates, spin, composition without fooling ourselves. So that history ladder, it begins with a beautifully simple idea from the middle of the 20th century. Planetary systems are messy builders. As young giants migrate and small worlds jostle, they fling out staggering numbers of icy fragments into galactic night. Decades later, reviews by David Dewitt and colleagues stitched the story together. If ejection is common, then the Milky Way should be full of such debris, and our surveys should eventually stumble upon a few first rarely, and then more often, as our cameras improve. It's reasonable to say that the first 2 detections, 1I Oumuamua and 2I Borisov, turned a theoretical population into a measured one. Now to the present ladder rung 3, I/ATLAS. The formal paper trail is reassuringly dull, which, in science, is a compliment. On the 2nd of July, the Minor Planet Center issued an electronic circular observations. From the 1st of July by the ATLAS station at Rio Hurtado in Chile showed a moving speck whose fitted path would not close on itself. Within hours, the orbit solved to a hyperbola, the signature of interstellar origin, and the object received both an interstellar designation, 3I, and a non-periodic comet name, C/2025 N1 ATLAS. That is the bookkeeping that turns astonishment into data. How exactly do you find something like this in the first place? The ATLAS telescopes are half-meter wide-field machines that sweep the visible sky from their sites in Hawaii, South Africa, and Chile, taking short exposures, subtracting yesterday's stars from tonight's and asking software to flag anything that moves. The same patch is revisited to build tracklets, little strings of detections that can be linked and fit to a preliminary orbit. With 4 stations scanning many thousands of square degrees per night, you gain the one thing serendipity always respects: coverage. The pipeline matters because the interstellar signature is subtle. At first, a new object looks like any faint near-Earth candidate. Only when you assemble multiple tracklets across nights does the fitted curve refuse to be a neat ellipse. Modern survey methods explicitly do this, linking testing trial orbits against the sky and weeding out false positives. You can think of it hand-wavy, but honest as solving a crossword where the same letters must satisfy several clues at once. When everything lines up only for a never-returning path, you allow yourself the word interstellar. From there, the baton passes to the broader fleet. NASA's public brief sets the basic geometry. 3. I reach its closest approach to the Sun around the end of October, at roughly 1.4 astronomical units just inside Mars's path, and it never comes, especially near Earth, staying roughly 1.8 astronomical units or more from us. That distance is both limiting and liberating. Limiting because it will never be bright to the naked eye. Liberating because spacecraft and large observatories can take their time. And they have. The Hubble Space Telescope resolved a tidy teardrop coma in late July, offering early constraints on the size of the solid nucleus and the character of the dust. Meanwhile, as the comet slid sunward its tail and surrounding cloud began to grow as you would expect when ice is warm and gas drags dust free, fresh images from the National Science Foundation's Gemini telescopes and related facilities showed precisely that behavior. That is not hype. That is the pattern we have measured for countless comets, only now the sample is from another nursery. If you've seen the headlines about a sunward jet, it's worth dissolving the paradox with a two-frame view. From our external perspective, radiation pressure and the solar wind do drive dust tails away from the sunday. But if an active vent faces sunward and launches grains at low-speed geometry, and grain size sorting can sculpt structures that in projection appear to point the wrong way. Experts emphasize that nothing supernatural is required. It is comet physics in a tricky viewing angle. In some sense, 3i is teaching us how easily perspective can fool us useful in a field where we infer everything from faint smudges. You might ask, how do we turn a fuzzy glow into numbers, the kind you can plot and argue about? There are a few well-worn handrails. Photometry of the coma and tail gives AFRO a parameter that roughly encodes dust production under simple assumptions about the grains. Narrowband spectroscopy in the visible and ultraviolet looks for fragments like CN and OH, the latter a daughter of water, letting us infer water production rates with models that have served since the early 1990s. In the infrared, we can chase carbon dioxide directly. In the millimeter arrays like ALMA, excel at carbon monoxide. The exact molecules will come down to signal to noise, but the methods are standard and they bridge beautifully to what we learned from 2I Borisov, whose carbon monoxide to water ratio was astonishingly high by solar system standards. Astrometry, the precise mapping of the comet's center against background stars, adds another quieter number, any non-gravitational acceleration caused by asymmetric outgassing. We learned with Oumuamua that even a tiny rocket effect can be measured if you collect enough positions over enough weeks. Whether 3i shows such a nudge and how large it is will constrain how evenly its vents are distributed and how vigorous its activity becomes near perihelion. Again, not hand-waving, that's a straight calculation on top of the orbit fit. There is a practical twist that delights me. 3i's path takes it to an awkward solar conjunction as seen from Earth briefly tucked behind the Sun, so ground-based observers have to pause. But that does not mean the comet vanishes from view. ESA notes that orbiters at Mars, like Mars Express and the ExoMars Trace Gas Orbiter, can watch from other vantage points, sampling the evolving coma while we wait for the geometry to improve. It's a reminder that our solar system is now threaded with observers. A rare visitor can be handed from world to world. If we step back, the structure is becoming clear. Surveys such as ATLAS find interlopers by relentless coverage and clever linking. The Minor Planets Center turns candidates into official objects with well-posed orbits. Space and ground-based observatories convert light into production rate sizes and compositions. And then the comparison begins. Do the ratios of water, carbon monoxide and carbon dioxide look like the comets we know? Or do they echo Borisov's cold storage chemistry? The answer will not only describe a single visitor, it will sketch the diversity of planet-forming disks across our galaxy. However, and I emphasize this as a scientist, we do not know those ratios yet with confidence for 3i. We have hints from colors and early spectra. We have geometry, driven oddities that are likely to settle as the viewing angle changes. And we have a short window near the end of October when activity may peak. That not knowing is not a failure. It's a research program you can write on a whiteboard. In the next part, I'd like to move from how we measure to why it matters, what 3i's chemistry can tell us about the temperature histories of alien protoplanetary disks, why non-gravitational nudges are a window onto a nucleus we cannot see, and how the coming era of the Rubin Observatory could turn rare interlopers into a small, honest sample of other solar systems. Now, why does the chemistry of 3i/ ATLAS matter, because ices are thermometers that remember. Water, carbon dioxide and carbon monoxide set in the nucleus like little time capsules, their relative amounts reflecting the temperatures and pressures where the comet's dust first clumped together. In the case of the earlier Visitor 2, I call Borisov, the ratio of carbon monoxide to water was astonishingly high by solar system standards, evidence that it formed in a far colder pantry than most of our homegrown comets ever knew. That conclusion wasn't hand-waving. It came from ultraviolet and space-based spectroscopy that directly measured fragments of water and carbon monoxide streaming from the nucleus, and from modelling that linked those fragments back to parent ices. The lesson was clear: protoplanetary disks around other stars do not all cook to the same recipe. With 3I, we have a chance to ask whether that cold storage story was typical or a glorious outlier. This time our instrument shelf is richer. The James Webb Space Telescope turned its near-infrared spectrograph toward the comet in early August. In that band, water, carbon monoxide and carbon dioxide each sing at different wavelengths. By stacking enough photons, we can separate their voices and estimate production rates. In truth, it may take careful modelling and multiple instruments to break degeneracies, but the point is that the data exist. Webb observed on the 6th of August, and the team has already circulated an initial preprint for the community to chew over. Even more delightful, our view isn't confined to Earth's line of sight. As 3I slip towards solar conjunction, from our perspective, European spacecraft at Mars Express and the ExoMars Trace Gas Orbiter took their turn. Their vantage offset by tens of millions of kilometres lets us watch how the coma and tail evolve as the viewing geometry changes. That matters because geometry governs what you think you see. A jet that appears to point sunward in our projection, a puzzle that made headlines, can dissolve into ordinary comet physics when you shift your angle. Low-speed grains launched from a sun-facing vent sunlight, sorting them by size, and the solar wind threading the expanding cloud. From one frame uncanny, from another familiar. And the beauty is that we can test the projection story because we have two frames. Those measurements will sit alongside the quiet numbers of astrometry. When you fit a precise path to many nights of positions, any tiny non-gravitational acceleration, a rocket-like push from asymmetric outgassing, shows up as a residual that you cannot explain away with gravity alone. If we see such a nudge in 3I, its magnitude and direction tell us about the distribution of vents across the surface, and indirectly about the spin state of a nucleus we cannot resolve. Put it this way, even when all you have is a fuzzy glow, the physics of momentum, conservation, and the patience to measure position after position give you a route to the hidden shape and behaviour of the core. Now to scale. It's reasonable to say that we still have only a handful of interstellar visitors in hand: 1I, Oumuamua, 2I, Borisov, and now 3I, ATLAS. But our tools for finding them are changing. The Vera C. Rubin Observatory in Chile has moved through first light milestones and is preparing to begin large-scale survey operations. Its legacy survey of space and time will sweep the southern sky night after night, linking faint moving points into orbits with software purpose-built for exactly this kind of needle-in-haystack problem. If the Milky Way is littered with interstellar debris, as theory has long suggested, then Rubin will transform rare luck into a small, honest sample, perhaps dozens over the coming decade, rather than a few per generation. That is not hype, that is the design brief, the cadence, and the control room now being readied for routine sky mapping. There is tucked inside the chemistry a deeper question about time. The European team following 3I has floated a striking possibility based on its trajectory through the galaxy. The object may be older than our solar system by a few billion years. If that inference holds as more data and dynamical tracing come in, we would be reading the ice-layered diary of a worldlet that condensed under a younger Milky Way sky. That does not make it mystical, it makes it valuable. The isotopic fingerprints of hydrogen in water, for example, the ratio of deuterium to hydrogen, are sensitive to formation conditions. Coupled with carbon to oxygen patterns and with the presence or absence of fragile organics, the ratios in 3I could tell us not just cold or warm, but how cold for how long and under what kind of starlight. In some sense, every volatile we detect is not simply a molecule, it is a clock. You might fairly ask, how do we keep our feet on the ground when the object is faint, the geometry awkward and the headlines noisy? The answer is beautifully dull. We triangulate. We combine independent lines of evidence, near-infrared bands from Webb ultraviolet fragments from space telescopes in Earth, orbit millimeter wavelines, from arrays such as the Atacama Large Millimeter divided by Submillimeter Array for carbon monoxide and visible light photometry for dust production parameters such as AFRO. Each has its own systematics. Together they constrain one reality. And when we are tempted by exotic explanations, we reach first for projection effects, grain size distributions and radiative forces, the catalogue of forces we know before we invoke anything new. That conservatism isn't timidity, it's how you keep the wonder honest. It's also fair to say that 3i is already teaching us how to coordinate. The Minor Planet Center's prompt circular turned a hint into a confirmed interstellar orbit within a day. Global facilities responded, national agencies stitched together vantage points from Earth and Mars, and space telescopes scheduled spectroscopy within weeks. Reuters and the Associated Press gave the public the essential geometry and the reassurance that the object would stay a comfortable distance from Earth, while agency pages kept observers posted as perihelion approached in late October. In a world where attention can be volatile, that steady relay from raw detection to careful context is part of the scientific achievement. So the why is this: each interstellar visitor is a data point on a map. We have only just begun to draw the temperature histories of alien disks, the chemistry of ices beyond our sun, the physics of dust and gas under different skies, and the simple statistical truth of how common such bodies are. And the how is equally beautiful: telescopes taking turns like musicians in a quartet, each playing its part of the spectrum, while the orbit fit keeps the tempo. In the next part, I'd like to follow that map outward to trace 3i's path through the galaxy with the tools of stellar dynamics, to ask what we can infer honestly about the kind of system that flung it away, and to explore a quiet, ethical turn that these visitors invite what it means on a small world around an ordinary star to read the mail of other suns and to treat that privilege with care. Let's try to read 3i/A TLAS, the way you'd read an old postcard whose ink has run. The postmark is the hyperbolic orbit that never returning curve stamped by the Minor Planet Center within a day of discovery. That's the bureaucratic way of saying this object does not belong to the Sunday. Now, if you ask, where did it come from? In the wider sense, the first clue is kinematic. Early reports had it arriving at roughly 37 miles per second from a direction close to the Milky Way's center-fast thin disk traffic, not a gentle drift from our own comet reservoirs. That's a handrail, not a conclusion. It tells you the inbound radiant in the sky and the speed at infinity that the orbit fit prefers. It doesn't yet tell you which star did the flinging. To move beyond the handrail, teams have taken the beautifully dull approach of stellar dynamics, integrate the comet's path backward through a model of the galaxy, and ask whether any known stars measured exquisitely by Gaia passed close, slowly enough to have mattered. A recent preprint did exactly that over 10 million years, comparing 3i's reconstructed track to Gaia DR3 stars with good velocities. The answer so far is no smoking gun. Dozens of close flybys were identified on nominal orbits, but none imparted a significant kick. The object looks kinematically consistent with thin disk populations without a nearby culprit we can point to. That's not a failure. It narrows the hunt and hints that the ejection probably happened far away and long ago, beyond the reach of present catalogues. There is, though, another stamp on the card composition. The James Webb Space Telescope turned its near-infrared spectrograph toward 3i on the 6th of August, and the first analysis now on the archive reports a carbon dioxide-dominated coma with water carbon monoxide and traces like carbonyl sulfide present too. The ratio of carbon dioxide to water appears exceptionally high by solar system standards at comparable distances from the Sunday. That points carefully to formation near a carbon dioxide ice line or to a history under harsher radiation than our comets typically experienced. It's fair to say this is the best chemical return address we've ever had for an interstellar visitor. This is where the dual-frame view earns its keep. From our perspective, the comet shows a puzzling sunward-pointing jet in some images, apparently backwards given that dust tails ought to stream away from the Sunday. From the comet's local frame, nothing magical is required. A sun-facing vent launches grains gently. Sunlight sorts them by size. Gravity and radiation pressure sculpt an arc that in projection from Earth looks like a tendril pointing toward the light. The headline calls it uncanny, the physics calls it geometry. And because we now have a second Vantage spacecraft at Mars, watch the comet during early October, we can test that projection story with a different viewing angle rather than an argument. Those Martian eyes matter for another reason. Three Eyes' path carries it behind the Sun from Earth's point of view for a short spell. Ground-based telescopes had to pause. But Mars Express and the ExoMars Trace Gas Orbiter were offset by tens of millions of kilometers and kept observing as the coma evolved near perihelion season. In some sense, we've learned to treat the solar system as an observatory with many balconies. If the view from one is blocked, another opens. If you prefer a human-scale image, picture this: a librarian trying to date an unsigned letter by the paper and ink because the sender's name is smudged. Carbon dioxide versus water is the paper stock. Trace organics are the watermark. Isotopes, if we can get them, are the tiny imperfections that fix a region at a time. Oumuamua gave us almost no chemistry. Borisov gave us abundant carbon monoxide and a classic tale. 3I is giving us carbon dioxide in force. A hint that planet-forming kitchens around other stars come in a variety of temperatures, and that what looks ordinary at first glance can be chemically exotic when you count the SAVE molecules. You might ask reasonably how sure we can be about the nucleus we cannot see. Two numbers help. First, the non-gravitational acceleration, a tiny rocket effect from asymmetric outgassing, will leave its fingerprint in the residuals of the orbit fit as we accumulate many nights of precise astrometry. Second, the dust production encoded in coma brightness parameters such as AF rho ties with assumptions to the surface area of active regions. Neither number is a photograph, but together they bound the problem. And here the community is coordinating in a way I find heartening. The International Asteroid Warning Network is organising a focused campaign through early 2026 to tighten astrometry standards on comets using 3I as a live, faint, moving target we all share. That's not glamorous work, but it's how raw wonder becomes measurable. Now, zoom out to the next decade. If theory is right, the galaxy should be seeded with staggering numbers of such shards, and the difference between rare and occasional is a camera that never sleeps. On Cerro Pachón, the Vera C. Rubin Observatory has already shown first images and is ramping toward full survey cadence, revisiting the southern sky every few nights with a 3.2 gigapixel eye. Rubin's search software links faint moving points into orbits by the million. It is reasonable to expect that once routine operations settle, we will go from 3 interstellar detections in 8 years to dozens over a decade. That won't just fill a list, it will let us ask population questions with a straight face. There is also a hint of choreography emerging between survey and intercept. Today, 3I is too distant and too swift for any craft we have on the shelf. But the lessons from its geometry and chemistry feed into missions built to loiter and pounce. ESA's Comet Interceptor, launching later this decade, is designed precisely to wait near the Earth-Sun L2 point and then sprint when a pristine or interstellar target appears. If Rubin becomes the finder and Interceptor the sampler, the next postcard from another sun might be one we open in our hands, not squint at from afar. I think it's fair to say the ethical turn is as quiet as it is real. When you can read the mail of other suns' ancient ices telling you about kitchens where worlds formed, you're reminded that our own world is an improbable island of meaning in a sea of debris. The right response is not hype, but care to measure honestly, to compare cautiously, and to keep wonder tethered to what the numbers will bear. So we have a hyperbolic postmark, a thin disk itinerary with no obvious sender, a carbon dioxide rich mix that points to colder kitchens or harsher skies, and a geometry lesson written as a sunward jet. In the next part, I'd like to take on the selection effects head on, why our first 3 interstellar visitors look so different from each other, what that might be telling us about the biases in our surveys, and how Rubin, Webb and Comet Interceptor together could turn strangeness into statistics. So, selection effects. It's reasonable to say they're the quiet puppeteers of discovery. We found one, Oumuamua, because a survey looking for near-Earth rocks happened to catch a fast, faint point of light with no visible coma. We found 2, I Borisov, because it behaved like a classic comet, outgassing early and loudly. And we found 3I/ATLAS, because an always-on wide-field system netted a moving fleck that later blossomed into an unmistakable coma. The difference in what they seem to be is not just nature, it's our ways of looking. Reviews by David Jewett and others have been explicit about this. With a sample this small, detection biases loom as large as the physics. Here's the simple, hand-wavy picture. An active interstellar comet announces itself by throwing dust and gas into sunlight, boosting its brightness by orders of magnitude. An inactive shard, by contrast, stays dull until it strays uncomfortably close. Surveys, therefore, over-report the gassy, dusty visitors and under-report the quiet ones. That is not a complaint, It's the geometry of reflection. Jewett calls it a data, limited field, reminding us to treat early patterns with suspicion until the numbers thicken. Now layer in motion. Interstellar objects move fast on the sky, often many tenths of a degree per day, so their images trail across a CCD in a single exposure. Trailing steals signal to noise and confuses software that expects star-like points. Synthetic population tests aimed at the Vera C. Rubin Observatory make the point cleanly. If you could magically remove the trailing loss and beef up the linking algorithms, you would immediately discover far more interstellar interlopers. The same simulations show a brutally wide range of expected yearly detections from roughly 0 to scores, depending on assumptions about size reflectivity and the steepness of the size distribution. In other words, the pipeline is part of the instrument. And then there's the Sunday, a surprising fraction of interstellar passers-by likely approach, from small solar elongations too near the Sun in our sky for ground telescopes to track. We preferentially catch those with fortuitous geometry and miss the ones that skim the dawn or dusk glare. One practical implication is that a space-based sentinel aimed safely closer to the Sun could harvest a different slice of the population. Several teams have argued exactly that in recent concept studies. But in the near term, the game changer is Rubin. First images in mid-2025 survey start not long after scanning the southern sky every few nights with a 3,200 megapixel eye. Expectations vary, some estimates are cautious, some bullish, but the direction of travel is clear, from rare accidents to small, honest samples. There's also a subtle phase angle bias. Comet dust scatters sunlight more strongly at certain angles, so a visitor can look ordinary from one vantage and spectacular from another. That is part of why 3I's early sunward feature caused such debate. From our external frame, tails should point away from the Sunday. From the comet's local frame, if a sun-facing vent launches relatively large, slow grains, then radiation pressure cannot immediately sweep them. The dust lingers in the orbital plane, and seen from Earth, when we cross that plane, it can masquerade as an anti-tail pointing sunward. That explanation is not exotic. It's a textbook projection effect that has shown up in well-observed solar system comets for decades. 3i gives us a way to test that story rather than merely assert it because we have more than one balcony on the same stage. When Earth slid into an awkward geometry, spacecraft at Mars kept watching offset by tens of millions of kilometers. A change from a sun-facing fan to a more conventional anti-solar tail as the geometry evolved would be exactly what the projection picture predicts. Early professional notes and community posts have been steering observers to that conservative view. It's fair to say that multiple vantage points turn paradox into calibration. Composition adds its own selection quirk. Gas species turn on at different temperatures. Water likes it warmer. Carbon dioxide and carbon monoxide can drive activity farther out. That means a comet with carbon dioxide-rich ices might look active at large heliocentric distances where a water-dominated nucleus would still slumber. 2i called Borisov taught us that carbon monoxide can dominate astonishingly so by inner solar system standards, implying formation in a very cold pantry. With 3i, James Webb has now reported a carbon dioxide-dominated coma with a carbon dioxide to water ratio among the highest ever measured at comparable distances. If you were designing a visitor to trigger our telescopes early, you would choose exactly that volatile mix. Nature seems to have obliged. The comparison with Oumuamua is instructive. In 2017, careful astrometry showed a tiny non-gravitational acceleration, as if a rocket were very gently firing. A cottage industry of explanations bloomed hydrogen ices, nitrogen ices, radiation pressure on an unusually thin body, each consistent with the data in some regimes and strained in others. The honest conclusion is that an inactive object gives you far fewer spectroscopic handles. The same bias that made Oumuamua difficult to spot also made it difficult to diagnose. 3i, by contrast, has handed us photons that whisper their molecular names. The puzzle shifts from, is anything there, to in what ratios and why? What does all this mean for the next decade? A reasonable conservative picture is this. Rubin will greatly expand our census, but which flavors it favors will depend on cadence linking and how well we recover trailed detections. Cautious forecasts suggest a handful of interstellar detections per Rubin year. More optimistic simulations assuming reflective Oumuamua-like shards and improved linking stretch to dozens per year. Even the low end is transformational when you are starting from 3. And because Rubin's alerts will be public, and fast space telescopes and planetary probes can pounce while chemistry is still readable. If we are careful, selection effects become a tool rather than a trap. By modeling the discovery pipeline end-to-end sky coverage, trailing phase angles, magnitude limits, and comparing the found objects to the detectable ones, we can peel back the biases and reconstruct the true underlying population, its size distribution, its velocity spread, its chemistry-driven activity. That is the quiet power of a survey era, statistics strong enough to subtract the telescope from the sky. Put it this way, the first 3 interstellar visitors look different, because nature is diverse and because our ways of looking are too. The trick now is to build a conversation between the two, use physics to predict what we should see, and use the survey to tell us what we actually do see, where those two-part ways the science lives. In the next part, I'd like to lean into that conversation to sketch how we turn 3. Eyes carbon dioxide-rich chemistry and measured dust dynamics into formation stories in alien protoplanetary disks, and to ask a gentle but important question, whether these drifting shards could have ferried the raw ingredients for life between suns and how we would know if they did. And let's turn 3I/ATLAS from a moving fleck into a formation story. A reasonable hand-wavy picture goes like this. In a young planetary disk, heat from the forming star falls away with distance, and different ices condense at different radii ice lines. Water freezes nearer in, carbon dioxide farther out, carbon monoxide beyond that again. The exact positions wander as the disk evolves, but the principle holds. The ratios of water, carbon dioxide and carbon monoxide that end up locked in a small body are a thermometer that remembers. Laboratory and modelling work back this up. Highly volatile species dissolve at tens of Kelvin while water waits for warmer conditions. So a nucleus rich in carbon dioxide or carbon monoxide hints at a pantry that stayed cold for a 2-7 long time or formed far from its star. If that is the kitchen, what are the recipes? One route is pebble accretion, dust grains coated in ices, stick settle and snowball. Another is the slow glue of collisional aggregation in a turbulent gas. Either way, you get layered material dust, mixed with ice, with pockets that awaken at different heliocentric distances as the sun warms them. That is why spectroscopy is precious. When sunlight hits 3, a gas escapes, drags dust with it, and each molecule sings at its own wavelength. By tallying those songs over time, we can ask, is the mix more like the water-driven comets we know, or more like the cold storage flavor seen in the earlier visitor? 2I Borisov. And because 3I is unambiguously interstellar, its orbit never closes, we are justified in reading its chemistry as a postcard from somebody else's nursery, rather than a recycled shard of our own. NASA's overview lays out those basics, plainly discovered by ATLAS in early July 2025, confirmed as interstellar within a day, and now a target for the whole spectral orchestra. Here's the dual frame move that keeps us honest. From our external perspective, the coma looks like a soft cloud whose brightness rises and falls. From the comet's local frame, the vents are real geography patches that switch on as sunlight strikes them and switch off as the nucleus rotates. The same physics that sculpts the tail also sculpts our inference. If carbon dioxide turns on earlier than water because it sublimates at lower temperatures, then 3I would advertise itself to our surveys sooner and farther out, biasing us toward noticing exactly this sort of chemistry. Selection effect and formation history intertwined. That is why we will need multiple apparitions in the coming years. Rubin's nightly sweeps converting rarity into a small, honest sample before we declare any one ratio typical. Rubin's remit is precisely to catch faint, fast movers, often enough to do statistics rather than stories. Now to the organics, the quiet, provocative part. We already know that comets can carry complex carbon compounds. A decade ago, the Rosetta orbiter's mass spectrometer at Comet 67P Churyumov, Gerasimenko, directly detected glycine, the simplest amino acid along with related amines repeatedly and unambiguously. If you prefer a more terrestrial proof, the Murchison meteorite, which fell in Australia in 1969, contains a menagerie of amino acids and even sugars. These are widely taken to be extrasolar system, or pre-terrestrial in origin, not contamination after the fall. The point is, plain comets and carbonaceous rocks are competent couriers of prebiotic chemistry inside a planetary system. Does that competence extend between stars? That is the delicate question often gathered under the banner of panspermia. Put it this way, the delivery of molecules seems straightforward. We have captured interstellar dust in aerogel, brought it home with the Stardust mission, and studied its structure and composition under microscopes. The delivery of microbes, by contrast, is the long shot. Space is a harsh laboratory. Ultraviolet light breaks bonds. Cosmic rays carve tracks through DNA. Vacuum desiccates. Experiments on the International Space Station, Japan's Tampopo series, is exemplary show that clumps of hardy spores can survive years when shielded, especially if embedded in rock or clay. Classic work by Horneck and colleagues reached similar conclusions. But millions of years, typical interstellar travel times, are a different regime altogether. Survival would require deep shielding and luck. It is not impossible in principle. It is not plausible in practice without very special circumstances. That is exactly why most astrobiologists speak cautiously organic chemistry is likely. Organisms are speculative. Even if microbes are out of reach, the chemistry they love is not. Amino acids, sugars, nitriles, simple aromatics, these can ride inside dust grains and ice mantles, withstand interstellar cold, and arrive as a feedstock wherever gravity welcomes them. In a young system, countless comets rain down on infant worlds. If just a fraction of those are interstellar, they could seed the pantry with useful reagents. None of this removes the need for a warm pond tides, mineral surfaces, or long patience. It simply broadens the supply chain. And it sets a testable agenda if 3 eyes ices and dust show familiar prebiotic fragments in familiar ratios that hints at a chemical universality across star-forming regions. If they look alien, that hints at multiple chemical dialects in the galactic conversation. The Rosetta detections give us the template for how to look. Interstellar samples, when we can catch them, tell us how far that template travels. There is a second, quieter test that 3i invites: momentum bookkeeping. Measure the tiny non-gravitational acceleration, the rocket effect of asymmetric outgassing, and you learn whether a few vents dominate or whether activity is spread more evenly. Tie that to dust production numbers and you back out a lower bound on the active area, a proxy for how much fresh ice is near the surface versus buried beneath refractory crust. Combine that with chemistry and you begin to invert a coma into a nucleus, not an image, but a set of constraints you can fail to satisfy if your formation story is wrong. That is good science, falsifiable, quantitative, dull in the best way. All this points to a choreography that did not exist a decade ago. A survey camera finds a fleck. A central clearinghouse posts the orbit. Within hours, big mirrors and space telescopes swing to the right wavelengths. Planetary orbiters watch from other balconies in the solar system. And soon a comet interceptor will wait in deep space ready to sprint if a pristine or interstellar target appears. In that world, strange is no longer a headline. It is a pipeline. The pipeline will tell us whether 3i's personality, its likely cold kitchen volatiles, its geometry tricky dust, its faint but honest coma is a common dialect or a regional accent in a galaxy of kitchens. I think it's fair to say the ethical turn follows naturally. If we are in a small way reading the mail of other suns, then the right stance is care. Care with claims, care with numbers, care with language that invites the public into the wonder without promising what the data cannot bear. We can be excited and precise at the same time. We can say molecules yes, microbes probably not, and then show our working. So we have a map ice lines as thermometers, spectra as recipes, dynamics as the librarian's date stamp, and a courier network that may reach, at least for chemistry, across the spaces between stars. In the next part, I'd like to push the dynamics further back in time, how exactly systems fling these shards away, what that implies for the population Rubin will see, and how the galaxy's tides and passing stars stir a slow river of debris that sometimes briefly runs right through our sky. Let's push the dynamics back to their source. A reasonable hand-wavy picture is that young planetary systems are wonderfully inefficient builders. Giant planets grow, migrate and scatter, and in the melee they fling away vast swarms of icy planetesimals. We believe our own system did exactly this. Numerical models and debris, disk observations suggest many other systems did too. The consequence is simple and beautiful. The galaxy should be threaded with expelled worldlets, largely unaltered since the day they were thrown out. That is not romance. That is the sober conclusion of decades of modelling anchored by what we now see around other stars. There are 2 broad routes for escape. In the first, a planetesimal is scattered by a giant planet onto an orbit whose furthest point lies in the tenuous outskirts of a system. Further tugs by the planet, by siblings, by a slowly changing disk, nibble away until the binding energy is gone. and the body slips into interstellar space. In the second, the object is fired straight out by a close gravitational encounter, in effect stealing a little of the planet's orbital energy. Both routes are messy, statistical, and relentless in a youthful system with giants. It is fair to say that any star with rambunctious planets becomes an exporter. Once free, these shards join a slow river set by the galaxy's kinematics. From our external perspective, most arrivals will share the thin disk's general drift tens of kilometers per second relative to the Sun, and will approach from a broad swathe of directions rather than one tidy radiant. 3I/ATLAS is a case in point. The initial orbit solutions report a hyperbolic excess speed of order tens of kilometers per second and a path unambiguously not bound to the Sunday. The numbers matter because they frame what surveys can hope to catch and how long we have to study a given visitor before it fades back into night. Now, an important aside on how often we should expect to see these messengers. After One Eye, the community tried to turn a single sighting into a number dense. A careful analysis of detection efficiency with the Pan-STARRS survey yielded a back-of-the-envelope figure of roughly a tenth to a few tenths per cubic astronomical unit, high enough that many stars must contribute. That estimate is debated, but it set the tone if even roughly right interstellar debris is not rare, only difficult to see. The subsequent synthetic survey studies aimed at the Vera C. Rubin Observatory make the point more bluntly depending on assumptions about size reflectivity, and especially how well software recovers trailed fast movers Rubin could find, anywhere from almost none to dozens per year. The pipeline is part of the instrument. The Rubin picture deserves a moment because it is the hinge between anecdote and statistics. Commissioning results and public briefings have been plain, with a 3.2 gigapixel eye and a cadence designed to revisit the southern sky every few nights. The Legacy Survey of Space and Time will give us, within its first seasons, a realistic sense of how common these interlopers truly are. The crucial caveat is not exotic, it is the trailing loss. Interstellar bodies slide quickly against the stars, smearing their light across pixels and defeating naive detection. Solve that algorithmic problem, link fast movers detrail cleverly, and you unlock a population. If ejection throws objects out, what throws comets in toward a system's inner rooms? Our own long-period comets tell the story. Far from the Sun, a tenuous halo of billions of bodies, the Oort cloud feels the faint but persistent tug of the galaxy's gravitational tide. That tide, combined with occasional close passages of other stars, can slowly tilt and stretch cometary paths until a fraction are dropped into the planetary region. It is a beautifully slow mechanism, worked out in classic papers in the 1980s, and deepened since the disk tide lifts perihelion stellar encounters knock on the door, and the result is a variable drizzle of visitors. The same physics that perturbs our cloud is stirring countless others, releasing stock into the interstellar river over cosmic time. Put it this way, ejection at the birth of a system fills the river. The galaxy's tides and fly-by stars keep it topped up. Some models even suggest time-dependent showers when a particularly close star brushes a cloud, enhancing the inward flux for a few million years before quiet resumes. The point for our present story is modest but powerful interstellar debris is not a one-off event from a single era. It is the background music of planetary systems living in a galaxy. Selection effects sit quietly inside the dynamics. A shard rich in volatile carbon dioxide or carbon monoxide can switch on far from the Sun and so advertise itself earlier to our telescopes. A dry compact fragment stays faint until it is too close and too fast to catch easily. The same population viewed through different algorithms looks like different natures. That is why forward models are indispensable. By injecting synthetic interstellar populations with realistic speeds and phase angles through a virtual Rubin, you can compare the detectable set to the underlying set and peel back the bias. Where the two disagree, you have learned something about both the sky and your instrument. There is also a gentle point about gravitational focusing. Massive bodies, especially the Sun, and to a lesser degree Jupiter, slightly bend the paths of passing interlopers, raising the encounter rate above the naive straight-line estimate. At the modest excess speeds typical of thin disk traffic, the enhancement is not dramatic, but it is real, and it subtly biases us toward noticing those that pass near the ecliptic and near the longitudes where our telescopes spend the most time. When we fold such focusing into synthetic surveys, it shaves the corners off our ignorance. What then does 3i teach us as a dynamical exemplar? First, that hyperbolic orbits with thin disk kinematics are exactly what you expect for a sample drawn from many senders over long times. Second, that a carbon dioxide forward chemistry will make an interloper conspicuous earlier and farther from the sun-tilting discovery toward this flavor of nucleus until our coverage and software improve. Third, that small differences in geometry phase angle line of sight through the dust fan can masquerade as odd physics unless you have more than one balcony on the scene. Each of these lessons is testable in the coming Rubin era. However, and this is the humility that keeps the conversation honest, our population inferences are still live. The order of magnitude number density suggested after Oumuamua could relax as better surveys and updated calibrations arrive, or it could harden if Rubin finds that faint fast movers were simply being missed. Either way, we will move from arguing over one or two case studies to comparing distributions, speeds at infinity, skyplane rates, activity onset distances, dust colors. That shift from stories to statistics is where astronomy becomes a branch of physics again. So, shards are flung by young giants. Tides and passing stars keep the river stirred. Our telescopes fish where and how they can. And 3I/ATLAS happens to be a catch that tells us both about the river and about the net. In the next part, I'd like to turn from dynamics back to craft how, in practice, we weigh and time a nucleus we cannot resolve. How we use non-gravitational nudges, dust production parameters, and color slopes to sketch the shape of a hidden worldlet. And how those sketches multiplied by many will let us say something honest about the diversity of other systems' kitchens. So, craft. How do you weigh and time a nucleus you cannot resolve? A reasonable hand-wavy picture is that we listen for physics hiding in the glow. The light from the coma sunlight, scattered by dust, encodes how much material is being lifted and over how big a patch. For decades, comet observers have used a simple, surprisingly useful parameter called AF-rho. You measure the flux from the coma in a small aperture, account for the sun's brightness and geometry, and roll the result into a single number that, under idealized assumptions, scales with dust production. It is not a photograph, it is a dial. Turn it over nights and weeks, and you watch the engine rev up and wind down as the comet approaches and leaves the sunday. That's not hand-waving, that's the definition of AF-rho, introduced by Michael Ahern and colleagues, and used ever since to compare comets honestly across telescopes and nights. Now, to the gentlest shove in nature, non-gravitational acceleration. If the nucleus is active in an uneven way, more jets on one side than another, the comet behaves like a tiny wayward rocket. The push is minute compared to gravity, but over many nights of precise astrometry, it leaves a fingerprint. The fitted orbit is a little off, unless you include a small direction-aware thrust. We learned the power of this with the first interstellar visitor, Oumuamua. Careful analysis showed a measurable extra acceleration that could not be explained by gravity alone. The details of the culprit in that case remain debated, but the method is solid fit the skyplane positions across an apparition and read the nudge from the residuals. If we see such a rocket effect in 3I/ATLAS, we will have learned something about how its vents are distributed on a nucleus we cannot yet image. Rotation is the next quiet signal. A spinning irregular body presents changing cross-section as it turns, even through a fuzzy coma that can imprint a light, curve a regular brightening and dimming, with a period that is to first order the rotation time. With care, and sometimes by catching the comet in a lull when activity drops, you can fold many hours of photometry to tease out that rhythm. Combine the amplitude of the variation with rough albedo assumptions, and you get constraints on the elongation of the nucleus, whether it is more potato than sphere. It's not as cinematic as a spacecraft flypast, but the technique has given rotation periods and shape hints for many comets, and is exactly the kind of patience 3I invites, especially when the coma thins after perihelion. Color too is a tool. Dust grains scatter sunlight more efficiently at some wavelengths than others. Measure the brightness through 2 or 3 broadband filters, and you can compute a spectral slope how red or neutral the dust is. Those slopes, expressed as a percentage per 100 nanometers, let us compare different comets on a common scale. In the broader comet family, redder dust often flags larger or more processed grains. Bluer or neutral colors can point to fresher, finer material. The important thing is not a single measurement, but change. If 3I's colors evolve with heliocentric distance or with viewing geometry that speaks to grain size sorting in the coma and to which vents wake first. Fold in polarimetry the way scattered light is polarized by irregular fluffy particles, and you gain sensitivity to porosity and aggregate structure. Put it this way, a handful of well-chosen colors and a polarization angle can tell you whether you are looking at airy clumps or compact chips. Of course, photons also carry molecules. Where AF-Rho listens to dust spectroscopy, names gases, water fragments into OH in the ultraviolet, carbon monoxide and carbon dioxide sing in the infrared and the millimeter. That is why the observing campaign on 3I keeps spanning bands. The Hubble Space Telescope has already shown a teardrop coma, the classic look of an active nucleus pouring dust into sunlight, while ground-based observatories and space telescopes pull apart the light to tally species. The geometry can be unkind, but the principle is straightforward. Count the photons at the right wavelengths, apply well-tested excitation models, and infer production rates, how many molecules per second are leaving the nucleus. Change those numbers over time and you begin to map not just what, but where and when on the hidden surface. There's a human craft element as well, decontaminating the signal. Comae are messy, starlight leaks into apertures, the nucleus is submerged under its own atmosphere. Observers gate their measurements with careful apertures, subtract the sky, and when possible, use aperture growth curves to check that AF-Rho has flattened as it should for a steady outflow. Spectroscopists dither along the tail, sampling on and off the coma to remove background and telluric features. Astrometrists employ centroiding algorithms tuned for trailed diffuse objects because 3I and its kin move fast enough to smear their light across pixels in a single exposure. None of that is glamorous. All of it is why the numbers can be trusted. A particularly useful interplay comes when you marry dust and dynamics. Suppose precise astrometry demands a non-gravitational term, pointing somewhat anti-solar. Suppose too that colours and polarimetry hint at larger, slower grains dominating the near-nucleus dust. That pairing would suggest vents in the hemisphere sunlit near perihelion, and grains heavy enough not to be flung instantly downwind by radiation pressure, exactly the conditions that can produce apparent sunward fans in projection, as seen in some early 3I images. The paradox dissolves into a geometry lesson you can test from different vantage points as the viewing angle changes. That is the beauty of building a basket of measurements that must agree. Each new data narrows the stories you are allowed to tell. And then there is the slow cumulative dividend consistency across tools. If the AF-Rho dial says the dust engine has doubled, spectroscopy should see a commensurate rise in gas. If not, your aperture may be too small or your model too simple. If the light curve period tightens as the comet approaches the sun, perhaps outgassing torques are spinning the nucleus up, the astrometry should then begin to ask for a slightly different non-gravitational term. If the color slope changes while the polarization does not, perhaps you have altered grain sizes without altering porosity. None of these alone is decisive. Together they sketch a nucleus that, though unresolved, is no longer a mystery so much as a constrained portrait. I think it's fair to say that 3I/ATLAS is a perfect teacher for this craft, precisely because it is faint, fast, and awkwardly placed. It forces us to use every balcony in the solar system, every wavelength we can reach, and every trick we have learned from a century of comets. Hubble's teardrop shows us the honest cometary nature. Careful orbit fitting will tell us whether the vents lean to one hemisphere. Color and polarization can whisper the texture of dust shed by an object born under another sky. And AF-Rho gives us a common yardstick we can carry from instrument to instrument, night to night. From these quiet signals, a worldlet emerges, never crisply, but clearly enough to test a formation story. So, we have the tools on the bench and a live target in the eyepiece. In the next part, I'd like to assemble a provisional portrait of 3 V6 from those tools: size, bounds, spin, hints, dust, character, and volatile mix. And then widen the frame to ask what this says cautiously about the diversity of kitchens that bake comets across the galaxy, and how Rubin's statistics will let us swap anecdote for population. Now let's assemble what we can say carefully about 3I/ATLAS, holding the numbers lightly but letting them guide us. First, the geometry. The orbit is unambiguously hyperbolic, so this is material from beyond our sun's family. The essentials, as NASA put it, are plain perihelion near the end of October, at roughly 1.4 astronomical units just inside Mars's path, and a closest Earth distance of roughly 1.8 astronomical units comfortably far, which is why this was always a scientific opportunity rather than a worry. That much is firm and already written down. Next, what it looks like. The Hubble Space Telescope's first resolved view gave us the classic cometary signature: a teardrop coma, sunlit dust flowing off an active nucleus, streaking against a background of trailed stars, because Hubble tracked the comet's motion. It is a small human thing, but I love that detail. The stars are smeared and the comet is still. It is the right way round for once. Chemistry is where 3i begins to sing its own tune. Early spectra from the James Webb Space Telescope report a carbon dioxide-dominated gas coma with water and carbon monoxide present, but by comparison, modest. The inferred carbon dioxide to water ratio, roughly 8:1 in those inbound data, sits at the very high end of what has been measured for comets at similar distances in our own system. A reasonable cautious reading is that activity is largely driven by carbon dioxide at these heliocentric distances, which tells you something about the kitchen where this nucleus formed cold enough or irradiated enough that carbon dioxide remained a principal volatile. That is not hand-waving, that is straight spectroscopy. Dust behaviour has been the source of the most headline-friendly strangeness, but it is also where projection can trick us. Some images showed a prominent sunward fan, which sounds backwards if you picture tails being swept away from the Sunday. The dual-frame view dissolves the paradox. A sun-facing vent launches relatively large, slow grains. Radiation pressure takes time to sort them. Seen from our angle, you can get a sunward-pointing wedge that later transitions into the familiar anti-solar tail as the geometry changes and smaller grains contribute. A new preprint by David Jewett and Jane Liu describes exactly that. Evolution, an early sunward fan, giving way to a classic tail, and even estimates grain sizes and ejection speeds, consistent with the sluggish response implied by radiation pressure. To my eye, that is the beauty here. The uncanny becomes textbook once you measure enough nights from more than one balcony. How big is the solid heart? We do not have a crisp diameter yet because the coma hides the nucleus, and our angle has been unhelpful. Bounds exist. Reporting based on Hubble photometry has suggested a range from hundreds of meters up to several kilometers. An honest admission that the current data admit multiple models for the dust and albedo. Treat that as a working box, not a conclusion. The range will narrow as post-perihelion activity eases and more rotational photometry becomes possible. What about the spin and the rocket effect? That tiny non-gravitational push from uneven outgassing. Those are the quiet numbers hiding in patient astrometry and light curves. If asymmetric jets dominate, the orbit fit will begin to ask for small thrust terms. If the cross-section wobbles with a period, a rotational rhythm will show up in the photometry. The community has queued up exactly that kind of work. In fact, the International Asteroid Warning Network has scheduled a late autumn through mid-winter astrometry campaign focused on comets using 3i as a test case to standardize how we measure fuzzy fast movers. It is gloriously unglamorous workshops on centroiding apertures backgrounds, but it is how wonder becomes numbers you can trust. A word on vantage. Our line of sight has been awkward at times, with a brief solar conjunction forcing ground-based observers to pause. But Mars did not have to blink when we did. ESA's Mars Express and the ExoMars Trace Gas Orbiter observed during our difficult weeks, giving a geometry-shifted view of the coma and tail. That second balcony does not only keep the record continuous, it lets us test projection, driven interpretations of jets and fans by watching features change with viewpoint. It is a small demonstration of a larger truth. The solar system is becoming an observatory stitched together by patience and radio links. If we try to sketch a nucleus consistent with these clues, a provisional portrait might read like this. A small unresolved body size, still uncertain, whose activity inbound is dominated by carbon dioxide. Vents likely preferentially sunlit near perihelion. Dust grains on the larger side, launched gently enough that radiation pressure takes its time. A morphology that evolves from a sun-facing fan to a more familiar anti-solar tail as the weeks roll on. Non-gravitational nudges perhaps present, but to be confirmed as the astrometric arc lengthens. It is neither a rebel nor a clone, just a coherent comet born under another sky, now behaving exactly as physics suggests it should when warmed by ours. Why does this matter beyond one postcard? Because each coherent sketch tightens the priors for the next. If carbon dioxide forward chemistry turns out to be common among interstellar visitors, then the outer zones of many disks are feeding the river. If instead we see a spectrum from water lead to carbon monoxide lead, then disks write in multiple chemical dialects. That is where the Vera C. Rubin Observatory changes the game. After first light images in June, Rubin's cadence is ramping toward the nightly surveys that will turn anecdotes into statistics, moving from 3 interstellar detections in 8 years to, with luck, dozens over a decade, provided we keep improving how we recover trailed fast movers. With statistics, we can ask population questions honestly: speeds at infinity, activity, turn-on distances, color slopes, volatile ratios. So a portrait has emerged, distance and safety well constrained, a teardrop coma that behaves, a carbon dioxide-rich recipe, dust that teaches geometry by seeming to point the wrong way until you change your angle, size still bracketed rather than measured, and a community deliberately turning strangeness into calibration, from Hubble and Webb to Mars-orbiting eyes and a worldwide astrometry drill. In the next part, I'd like to take that calibration and push it outward. What a true census in the Rubin era would let us say about how planetary systems eject their debris, why some disks seem to bake sweeter or colder comets than others, and how a loitering comet interceptor at the Sun-Earth L2 point could, for the first time, meet one of these wanderers in person. What would a true census look like? I think it's fair to say it begins when anecdotes give way to nightly routine. On Cerro Pachon, a wide eye is opening the Vera C. Rubin Observatory, with a cadence built to sweep the southern sky again and again, turning faint, fast flecks into linked orbits and honest statistics. Synthetic surveys run through Rubin's software make a clear if sobering point. The biggest bottleneck is not the darkness of the objects, but their speed across the sky. Trailing spreads their light across pixels. Naive algorithms miss them. Fix that link trail, detections better detrail cleverly, and the predicted yield jumps from essentially none in a poor year to scores in a good one. The range is wide because we do not yet know the true albedos and size distribution, but the direction of travel is unmistakable, from 3 confirmed interstellar visitors in 8 years to dozens over a decade, if we do the software as carefully as the steel. That is not hand-waving. That is the explicit conclusion of simulations targeted at Rubin's cadence. What does a census buy you beyond a longer list? First, the power to speak in distributions rather than anecdotes, speeds at infinity, activity, turn-on distances, color slopes, and volatile ratio. Second, the leverage to peel away selection effects. If carbon dioxide-rich nuclei tend to announce themselves farther out, a Rubin sample will quantify that bias, letting us reconstruct the true mix of water-led carbon dioxide-led and carbon monoxide-led bodies in the galactic river. Third, the pairing with spectroscopy. Rubin will raise the flag. Space observatories and large ground-based telescopes can then pounce while the chemistry is still readable. That choreography is already playing out with 3 I/AT-LAS, the hyperbola and safe geometry from orbit fitting, the teardrop coma from Hubble, and the carbon dioxide dominant recipe from the James Webb Space Telescope's near-infrared spectrograph. The lesson is method, as much as result alerts fast follow-up, faster numbers cautious. A census also sharpens the old question, where do these shards come from? With enough paths and speeds, you can run the movie backwards through a model of the galaxy, asking whether any known stars measured exquisitely by Gaia cross near the census. Reconstructed tracks. For a few there will be suggestive convergences. For most there will not, because the ejections are ancient and the uncertainties grow as you integrate backward. That is why chemistry matters so much when dynamics cannot give you a return address. ICEs sometimes can. Already Webb's inbound spectrum of 3 I reports a carbon dioxide to water mixing ratio of roughly 8:1, among the highest measured at comparable distances, for any comet, suggesting either formation near a carbon dioxide, ice line, or long residence under harsher radiation than our homegrown comets have known. It is a beautifully specific hint from a faint glow. But there is a second hinge between anecdote and census, and it is hardware with patience. Comet Interceptor, a European mission with Japanese partnership, is being built to ride to the Sun-Earth L2 point in the late 2020s and then wait. The plan is disarmingly simple: loiter in the cool dusk of L2 until a pristine long-period comet, or, in the best case, an interstellar visitor appears on a reachable trajectory, then sprint. Multiple spacecraft elements will separate for a fly-through, giving us multi-point views of nucleus, jets, and coma. Launch is planned for the year 2029 on an Ariane 6-2 alongside the Ariel mission. The destination is an as-yet unknown target found by surveys like PAN, STARS, ATLAS, and crucially Rubin. In other words, the census becomes a trigger for the handshake. If that sounds a little like fishing from a pier, that's because it is. But the pier is well chosen. L2 sits 1.5 million kilometers sunward of Earth, a quiet radio-lit balcony with a wide field. From there, Interceptor can pivot when Rubin and its kin raise the alarm. The prize is not spectacle, it is ground truth. A flyby would turn the dials we currently infer, active area vent distribution, grain sizes, into images, mass spectra, and resolved jets. The sunward fan that caused such debate in early 3I imagery beautifully explained as a projection effect once Hubble Mars-based and ground-based views were compared, would be mapped in 3 dimensions in a single pass. And if the target were interstellar, we would for the first time sample other system ices and dust in situ. That would move an entire field from best fit models to measured reality. Even before an intercept, we are learning to think like a distributed observatory. When Earth's view of 3, I was lost in the sun's glare. Mars took the baton. Mars Express and the ExoMars Trace Gas Orbiter watched as the coma evolved from a different angle, testing the idea that the early sun-facing feature was geometry rather than new physics. ESA went further, floating a bracing thought that, judged by its galactic trajectory 3, I could be older than the solar system by billions of years, a suggestion to be handled gingerly, but one that underlines why composition is a kind of the clock. These are the habits of a maturing craft. Share the sky, compare frames, and let the more cautious explanation win when it fits the data. Sensors work is not just glamorous alerts, it is also calibration. The International Asteroid Warning Network has just announced a comet astrometry campaign bracketing late November to late January, using 3 I/ATLAS as a shared faint fast target to teach and test how we measure the centroids of fuzzy things that move. Workshops, checklists, and uniform reductions may sound dull. They are how non-gravitational accelerations become believable and how tiny torques from outgassing become measured rather than guessed. In a survey era, communal good habits beat lone cleverness every time. Let me put the whole arc in one image. Imagine an index rather than a postcard rack, each interstellar visitor a line, not a headline. Rubin fills the index. Hubble and Webb write chemical and dust notes in the margin. Mars, side and Earth, side vantage points annotate geometry. IAWN keeps the page neat, the numbers legible. And when luck smiles, Comet Interceptor draws a ring around an entry and we go to meet it. Somewhere on that page sits 3I with its hyperbolic postmark, its carbon dioxide-rich scent, and its early sunward fan that turned out to be a patient lesson in perspective. The point is not that it was stranger than we imagined, but that our ways of looking kept making it stranger until we did the work. So, with a census in reach and a handshake being built at L2, we can ask bolder questions without abandoning humility. How diverse are the kitchens that bake comets across the galaxy? Are carbon dioxide forward recipes common, or are we just noticing them first? Does the thin disk river deliver a steady drizzle, or will we see clusters that hint at stirring by passing stars? In the next part, I'd like to take that last question seriously, walking through what the galaxy's tides and the local stellar traffic might be telling us about when interstellar visitors arrive, and whether 3I's timing is, in some modest, testable way, a message about our neighborhood rather than a coincidence. When the river rises, tides traffic and timing. Is there a season to our surprises? It's reasonable to say that interstellar visitors do not arrive like raindrops, strictly random and uncorrelated, but more like a river whose level is set by slow forces and occasional upstream weather. 2 quiet mechanisms stand out. One is the galactic tide, the faint, persistent tug of the Milky Way's disk on the distant reservoirs of comets that encase many planetary systems. The other is the traffic of passing stars, each encounter nudging those reservoirs, sometimes gently, sometimes with enough insistence to spill a few bodies into interstellar night. Classic work in the mid-1980s showed how the vertical component of the galaxy's gravity slowly tilts and stretches comet orbits in an Oort-like cloud, lifting some perihelia and lowering others over millions of years. The result is a background drizzle of long-period comets toward the inner system. That's not romance, that's the calculation. Now add local traffic. Every so often a star brushes past with just the right combination of distance, speed and mass to stir the cloud more vigorously. We have a recent and beautifully documented example. Schultz's star, a dim red dwarf plus brown dwarf pair, passed through the outer Oort cloud roughly 70 to 80,000 years ago at a closest approach of order. 52,000 astronomical units, about a quarter of a parsec. The encounter was dynamically weak, too small to spray comets at Earth on human timescales, but it was real, and it was measured by integrating the motions of the sun and the star through a galactic potential. Even a mild brush like that reminds us that the solar system lives in a crowded suburb where neighbours amble past every now and then. There is a future neighbour we already have penciled into our diary, Gliese 710. With the help of Gaia's exquisite astrometry, several teams have refined its predicted approach, and it appears likely to pass within roughly 10,000 astronomical units in about 1.5 million years. That is inside the Oort cloud proper. The encounter will not be apocalyptic. The speeds and masses keep it gentle, but it should noticeably perturb the distant comet reservoir, raising the inward drizzle for a time. The broader point is modest, but powerful comet flux is time-dependent, modulated by the slow tide of the galaxy, and salted with the occasional season of stirring when a star passes a little too close. You might ask fairly what any of that has to do with interstellar objects like 3I/ATLAS that are already unbound. The link is origin and supply. The same scattering that populates an Oort cloud during a system's youth also ejects vast numbers of bodies completely, especially in systems with rambunctious giant planets. Over billions of years, galactic tides and stellar flybys then keep peeling the tenuously bound off the top of those clouds. The upshot is a slow river of debris drifting with the local thin disk traffic. From our external perspective, typical relative speeds at infinity sit in the tens of kilometers per second, thin disk kinematics tied loosely to the local standard of rest, and arrivals come from broad swathes of sky rather than a single radiant. That is exactly what we have measured so far for interstellar interlopers. There's a neat dual-frame view that dissolves a potential paradox about clustering. From our ground-based survey limited frame, we might see bursts of discoveries, several fast movers in a year, then a lull. From the galactic frame, the underlying flux may be nearly steady. The burst is a property of our net, not the river. Two ingredients bias our catches: geometry and soft geometry, because many arrivals hug small solar elongations lost in twilight glare, and we only glimpse the ones that slip into darker sky. Software, because fast movers smear their light across detector pixels, lowering signal to noise and confusing linking algorithms. Simulations tuned for the Vera C. Rubin Observatory make the point bluntly: if you could magically remove the trailing penalty or link trail detections more cleverly, the predicted interstellar yield leaps from almost none to scores per year, depending on assumptions about size albedo and the slope of the size distribution. In other words, the timing in our notebooks is partly us. Still, the sky has a say. The galactic tide cycles, comets over characteristic times measured in tens to hundreds of millions of years, and the statistics of stellar flybys, how often a star passes within a quarter of a parsec, say, set a loose cadence for episodes of enhanced stirring. Schultz's star is a reminder at the gentle end. Gliese 710 will be a reminder at the not-so-gentle end a million and a bit years from now. Put it this way, the river's base level is tidal, the ripples are passing stars. Our catches will reflect both with the extra modulation of weather in our software. There is a subtle diagnostic hiding in the speeds of what we find. Objects born and ejected in the thin disk, the calm traffic of the Milky Way's midplane should arrive with modest excess speeds, tens of kilometers per second relative to the Sunday. Bodies flung from hotter populations, the thick disk or even the halo, carry larger dispersions, 50 to 100 kilometers per second or more, for the thick disk, hundreds for the halo. The first three interstellar visitors fit comfortably in the thin disk picture. A Rubin-era census will test whether that remains true. A tale of faster interlopers would whisper of more exotic birthplaces. That's the benefit of statistics. Velocity distributions tell stories that single objects cannot. And then there is gravitational, focusing the quiet amplifier. As an interstellar body threads the solar system, the sun's gravity bends its path slightly, raising the effective encounter rate above a straight line estimate. Jupiter adds a smaller bias. At the thin disk speeds we have discussed, the enhancement is modest but real. Fold that into synthetic surveys, and you learn two useful things. First, that our all-sky cameras are indeed fishing in a mildly converging flow. Second, that the preference for certain sky longitudes and ecliptic latitudes is not just where we look, but how the river bends near the Sunday. It is a small correction, but in a data-poor field, small corrections matter. What does all this mean for 3I? Caution first, one comet does not time a tide. But its comfortable thin disk speed, its hyperbolic postmark, and its carbon dioxide forward chemistry are exactly the sort of data points we need if we are to turn the river flows into the river flows this way. Dynamics tells us the drift. Chemistry tells us the kitchens feeding it. If the next dozen interstellar detections continue to show volatile mixes that wake up far from the sun, then the outer zones of many disks may be the main contributors to the flux we see. If instead we begin to catch more water-led visitors closer in, we will have learned as much about our net as about the river. I think it's fair to say the deepest comfort comes from the timescales themselves. The galactic tide that lifts comets has been lifting them since the sun was young. The passing stars were always passing. We are not witnessing an anomaly, but noticing a background pattern that was there all along. and that we are finally equipped to measure patiently, routinely, and with enough honesty to separate the sky's rhythms from our own. So, the tides set the base level, the neighbours add ripples our software chooses when the bell rings, and 3I/ATLAS happens to arrive while our instruments are learning to keep time. In the next part, I'd like to ask a gentler, human-sized question that follows naturally from these grand cycles. What responsibilities come with opening the post from other suns, how we share uncertainty, how we name and frame discoveries, and how we fold this new steady river of elsewhere into our picture of a small bright world and the lives upon it. Now, if you open the post from other suns, you owe the senders and your neighbours a little care with language. Wonder is earned with numbers, not headline adjectives, and uncertainty is not a flaw, it's the shape of the frontier. So let me begin with the plain facts we can anchor to before we spiral outward into metaphors. The Minor Planets Center issued the formal confirmation. Within a day of discovery, the path is hyperbolic, never to return, and the object carries two names at once. Its interstellar designation, 3I/ATLAS, and its comet style. Bookkeeping C/2025 N1 parentheses ATLAS. That's the administrative skeleton on which we hang our curiosity. There's also a careful tradition about what we call things. In 2017, the International Astronomical Union approved a new scheme for interstellar interlopers, a Roman numeral I for interstellar, preceded by a running count, 1 I for the first, 2 I for the second, and so on, and where appropriate, a culturally resonant name proposed by the Discovery team. That's why the first was 1I/Oumuamua, a messenger from afar, arriving first in Hawaiian, and the second 2 I/Borisov after its discoverer. The third, by contrast, retains the survey's label. It reminds us that this is a population we're beginning to count, not a cast of characters we're minting into myth. Names steady the hand. Next, the geometry, the bits that keep the public safe and the science honest. NASA's plain language page has been useful here. Closest approach to the Sun around the end of October, at roughly 1.4 astronomical units just inside Mars's orbit, and an Earth mist distance of roughly 1.8 astronomical units, in other words far. That framing matters because when a comet is faint and the picture's a pretty speculation rushes in to fill the silence. Better to put the distances on the table, let the shoulders drop, and then get on with the fun. What counts as fun scientifically is often provisional. Some of the most interesting early numbers come as preprints, community drafts that haven't yet run the gauntlet of peer review. In August, a James Webb team posted a spectrum that, if it stands, places carbon dioxide front and center in 3I's coma, with water and carbon monoxide present but comparatively modest. They even quote a carbon dioxide to water mixing ratio of roughly 7 and a bit to 1, describing it cautiously as among the highest seen at similar solar distances. NASA's own research note echoed that headline, water, ice and vapor detected carbon dioxide dominant. That is the kind of claim I like auditable molecule by molecule and bracketed by error bars. But we keep our language soft until the method notes have been argued over in print. We also owe people perspective when images mislead. Some early frames showed a prominent sunward fan, which sounds paradoxical if you carry in your head the rule tails point away from the Sunday. The projection dissolves the paradox. If a sun-facing vent tosses out comparatively large, slow grains, radiation pressure takes time to herd them. From our angle, you can easily draw a fan that appears to point toward the light. A second balcony, this time from Mars orbit, helped clinch that conservative reading, giving a different line of sight as the geometry evolved. Again, not wizardry, just comet physics plus viewpoint. And this is where institutions quietly earn their keep. The Minor Planets Center does the dull heroism of orbit clearing. NASA and ESA offer public pages that lead with distances and dates. And the International Asteroid Warning Network, a United Nations endorsed collaboration, has spun up a comet astrometry campaign that uses 3I as a common faint moving target for sharpening how we measure fuzzy things. Workshops, uniform methods, shared reductions, not glamorous, but this is how I think it's doing X. Becomes to within the quoted uncertainty it is doing X. It's also how 1,000 small telescopes become one coherent instrument. It's reasonable to say that alongside the careful work there will always be noise claims of strange alloys and covert alarms, whispers of artificiality. The antidote is not scorn but context. Reuters' early piece laid out the basics: discovery date, speed-safe, distance, perihelion timing without embroidery, and NASA's page sticks to the same discipline. When more flamboyant outlets drift toward unfalsifiable stories, the right move is to bring the conversation back to what the instruments can actually test: molecules at specific wavelengths, dust colours and polarization, positions on the sky night after night. Extraordinary claims deserve an observing plan, not a shrug. There's also a responsibility in how we sequence the story. A good rhythm is what we know, how we know it, what we don't know, and how we'll find out. For 3, I that might read, we know the orbit is interstellar and the pass is distant. We know there's an active coma with a lightly carbon dioxide forward chemistry. We don't yet know the nucleus size or spin to better than broad brackets. We will find out by extending precise astrometry to sense tiny non-gravitational pushes, by watching the colour and polarization of dust as the geometry changes, and by revisiting the spectrum as the comet warms. If I were writing a chalkboard in a lab, those would be the bullet points. The public deserves exactly the same chalkboard, minus the jargon. Finally, a word about names and wonder. I like that 3i/ATLAS carries its origin story in the label, a reminder that a modest survey in Chile and Hawaii is now part of a galactic conversation. I like that the rules for naming were decided before the headlines, and that the distances and dates lead the public pages. And I like that the community is willing to say we don't know in one breath and here is how we'll know in the next. That humility is not performative, it's how you keep the horizon wide. So, if we do our housekeeping, clear labels, cautious numbers, open methods, the strangeness of 3i stays where it belongs in the physics and the chemistry, not in the noise. And with that housekeeping in place, we can return to the deeper question that the molecules are whispering. In the next part, I'd like to walk the chemical ladder outward, what carbon dioxide forward comets imply about ice line locations, how different stellar types bake different recipes, and whether with a Rubin-era census in the hand we might begin to say carefully how typical our own solar system's kitchen really is. Starting next, let's walk that chemical ladder outward. If 3i/ATLAS hums with carbon dioxide, what does that whisper about the kitchen where it baked? A reasonable hand-wavy picture is that every young planetary disk has ice lines or snow lines where different volatiles freeze out as you move away from the infant star. Water freezes nearer in, carbon dioxide farther out, carbon monoxide farther still. Those lines are not fences. They wander as the disk cools and as grains drift. And there's a subtlety we've come to appreciate. Volatiles can be trapped inside other ices, so the carbon to oxygen chemistry we read later is a blend of temperature, history, and sequestration, not a single thermostat. In other words, water here, carbon dioxide, there is a helpful first sketch, but the real map has eddies and backwaters that models now try to include. With that in mind, the early James Webb spectrum of 3.1 is striking. On an August night, the near-infrared spectrograph caught a carbon dioxide-dominated coma, with water carbon monoxide and a few traces carbonyl sulfide among them humming more softly. The headline number, the carbon dioxide to water mixing ratio of roughly 8:1 at a heliocentric distance, just beyond 3 astronomical units, puts 3i at the extreme carbon dioxide rich end, compared with comets at similar distances in our own system. That can mean at least 2 things. Either the nucleus is intrinsically rich in carbon dioxide because it assembled near that ice line in its parent disk, or sunlight is failing to penetrate deeply enough yet to wake abundant water, ice, leaving the colder volatile to drive the activity. Both are testable as the comet warms and we gather more spectra. Contrast that with 2 I called Borisov, whose chemistry shouted carbon monoxide. Millimeter wave and ultraviolet work during 2019 and 2020 found carbon monoxide production rates outpacing water by vast factors unusually high, by inner solar system standards pointing to formation in a very cold pantry or to long-stored ices that never saw much stellar heat. Between Borisov's carbon monoxide and ATLAS's carbon dioxide, we already have 2 different recipes from 2 other kitchens. Add in a growing census and the chemistry becomes population, not anecdote. Now stars matter. A disk wrapped around a cool red dwarf bakes differently than a disk lit by a young hot star. The location of the water, carbon dioxide, and carbon monoxide snowlines slides inward or outward with luminosity. Ultraviolet radiation changes how easily organics are broken and remade, and the dust grain traffic drifting pebbles that carry ices inward and outward blurs any single radius into a zone. Laboratory and modelling work has shown that trapping water, ice caging, carbon dioxide say, can push carbon to oxygen ratios around in ways we must account for if we want to turn a comet's present-day mix into a birth certificate. 3. I's carbon dioxide forward signature then could reflect a luminous parent star that held the carbon dioxide line farther from home, or simply a disk where trapping and transport did the heavy lifting. The physics is messy. The point is that we have the knobs to turn in our models and the photons to test them. There's a useful dual-frame view here too. From our external perspective, 3i advertises itself early because carbon dioxide sublimates at lower temperatures than water, so it switches on while still far from the sun, making discovery more likely. From the comet's local frame, the vents are just geography waking with dawn. The selection effect and the formation story are tangled together. A population with more carbon dioxide-rich nuclei will be overrepresented in our current catches, all else equal. That is not a flaw. It is information so long as we do the statistics honestly. And that is where the Vera C. Rubin Observatory changes the conversation. After its first images in late June of 2025, Rubin is ramping towards survey cadence. Simulations aimed at its pipeline suggest that once trailing losses and linking are tamed, yearly detections of interstellar interlopers could range from a handful to dozens depending on albedo and size distributions. With that many, we can correct for the very biases that helped us notice 3i in the first place. If we imagine the next few years as a matrix, chemistry sits on one axis and dynamics on the other. Chemistry, water-led, carbon dioxide-led, carbon monoxide-led. Dynamics speeds at infinity, sky plane rates, non-gravitational nudges that hint at vent patterns. Fill enough boxes and patterns emerge. Perhaps carbon monoxide forward bodies prefer slightly higher approach speeds because they come from colder, older populations. Perhaps water-led bodies skew to slower, brighter apparitions and we've been missing them in twilight. The delight is that those are not barstool speculations. They are testable with an alerting survey and prompt spectroscopy. 3. I's 8:1 carbon dioxide to water is the first tile in what could become a mosaic. What about the organics, the molecules that make headlines because they whisper of kitchens like ours? We already know from the Rosetta mission that glycine and related amines can be liberated from the dust and ice of a cometary coma. That was a clean, repeated detection at 67P Churyumov-Gerasimenko by the orbiter's mass spectrometer. If a future intercept mission were to fly through the wake of an interstellar comet and sniff similar volatiles, ammonia-bearing molecules, nitriles, simple aromatics, in familiar ratios, that would argue for a chemical universality across star-forming regions. If instead we found a markedly different pantry, it would argue for multiple dialects of prebiotic chemistry in the galaxy. 3. I's carbon dioxide forward profile does not answer that on its own. It simply tells us where to point the mass spectrometers when the day comes. You might ask fairly whether our solar system is typical or whether we are reading a peculiar dialect as if it were the language. The honest answer for now is that we don't know. 2 data points with very different volatiles argue for diversity. A census with dozens will let us say something more precise. Perhaps our water-led comets sit comfortably in the middle of a spread defined by carbon dioxide on one side and carbon monoxide on the other. Perhaps we are the outlier, and the galaxy prefers colder kitchens. Rubin's job is to find the bodies. Our job is to keep the comparisons rigorous, same distances from the sun, same methods, same error bars, so that typical means something other than familiar. And there's one last handrail that keeps me calm when the headlines warm up. The basics are well constrained. 3i's path is unambiguously hyperbolic. Perihelion sits just inside Mars's orbit near the end of October. Earth remains comfortably distant. Those are the bookends within which the chemistry becomes interesting. So we keep doing the dull, beautiful work orbit fits photometry spectra. We fold selection effects into our models, and we let a small river of visitors from elsewhere teach us which kitchens are common and which are rare. A carbon dioxide-rich postcard from another nursery, a theory of moving snow lines and trapped volatiles, a survey ready to turn anecdotes into distributions. In the next part, I'd like to follow the hardware from Rubin's alerts to a loitering comet interceptor at the Sun-Earth L2 point and sketch how for the first time we could meet an interstellar visitor in person, comparing what the spectra promise with what dust counters and images we'll actually see when we fly through the wake. So, hardware. If Rubin is the bell that rings when a stranger steps into the hall, Comet Interceptor is the hand we've been building to reach out. The idea is beautifully simple. Launch a compact multi-part spacecraft to the Sun-Earth L2 point. a quiet gravitational balcony 1.5 million kilometers from home, and let it wait. When a pristine long-period comet appears, or if we are very lucky, an interstellar visitor on a reachable path, the craft's sprint separates into 3 pieces near the target and gives us a multi-point view of the nucleus, the jets, the dust and the plasma all at once. ESA's outline is spare and clear launch in the year 2029 on an Ariane 6 2 ride-sharing with the exoplanet mission aerial park at L2 and await the alert. The architecture matters because it solves a real problem of perspective. One main spacecraft called A flies the safer path and acts as a communications hub. 2 smaller probes B, one from JAXA and B2 from ESA, peel away to thread closer lines through the coma. 10 instruments across the trio form a deliberate ensemble high-resolution cameras to map the surface, wide-angle and all-sky images to read the spray of dust, a dust fields, plasma suite to feel the environment, and mass spectrometers and infrared sensors to weigh and name the escaping gases. It's not hand-waving. ESA's instrument pages and mission papers list the set explicitly down to names: COCA, the comet camera on spacecraft A, a dust fields and plasma suite on A, and again on B2, a narrow and wide-angle camera pair on B1, NVIS, an entire visible sky coma mapper on B2, and in the core science lineup, a mass analyzer for neutrals and a multispectral infrared sensor to turn glow into molecules and temperatures. The point of 3 spacecraft is a 3-dimensional story, not a single postcard. If you want a hand-wavy but honest picture of the encounter, imagine choreography rather than a charge. Weeks before closest approach, the small probes detach and drift to their slightly different lanes. B1 Japan's contribution carries a Lyman alpha hydrogen imager to map the vast water-made halo and a plasma suite magnetometer plus ion mass spectrometer to feel the shock where solar wind meets comet breeze. Its narrow and wide-angle cameras handle the close-in shape and the broader dust structures. B2 ESA's smaller companion brings an all-sky polarimetric coma mapper and the OPIC imager for navigation and science, again paired with dust and plasma sensors. Meanwhile, spacecraft A keeps its distance, steering the radio link and sweeping the nucleus with COCA and the thermal infrared sensor to tie temperatures to terrain. That is not me speculating from first principles, it is the mission design written down by the teams. Now link that to our puzzle with 3 I/ATLAS. You remember the early Sunwood fan that made headlines, the feature that looked backwards until geometry explained it? Interceptor is built to turn that kind of projection paradox into measurement. With 3 vantage points crossing the wake, the dust grain sizes and launch speeds stop being guesses. Polarimetry across the whole sky tells you how fluffy the grains are. The dust sensors count impacts as a function of mass. The plasma suite watches the magnetic field drape and kink around the outflow. If a sun-facing vent is launching large, slow grains that take time to be herded by radiation pressure, the 3 probes will literally fly through different parts of that arch and measure it. The dual frame story becomes a tomogram, a layered map rather than an argument. And the chemistry, this is where the mass spectrometers earn their space on the bus. Webb's inbound spectrum for 3 are reported a carbon dioxide dominant coma with water and carbon monoxide present, but quieter, and a carbon dioxide to water ratio near 8:1 at a few astronomical units from the Sunday. With Interceptor, the mass analyzer for neutrals and the mid-infrared sensor would take that spectral hint and turn it into a local inventory: carbon dioxide, water, carbon monoxide, the small sulfur-bearing and nitrogen-bearing species, and if luck holds, a handful of fragile organics in familiar or unfamiliar ratios. Tie those abundances to temperature maps from the thermal sensor and to images of the vents, and you finally have the thing we're always skating around with: ground-based spectra, a map of what is coming from where on the surface. Safety and pragmatism sit under the hood. A fly-through of an active coma at tens of kilometers per second is not a Sunday drive. You build dust shields that act like layered catcher's mitts. You choose approach vectors that keep the worst of the jetting to one side. You accept that the close probes are expendable if the science return justifies the risk. This too is written down. The dust and field suites are explicitly designed to survive and count impacts while keeping the spacecraft attitude stable. And even the shielding design has a literature now with modern takes on Whipple-style armor and aerogel stuffing to spread out the punch of a grain. It's engineering in service of curiosity. If you ask why wait at L2, the answer is time. By the time a truly pristine long-period comet is discovered inbound from the deep, there is rarely enough calendar left to design, build, and launch a bespoke mission. Parking at L2 buys you years of patience, and a quick sprint when Rubin Pan-stars a TLAS or their kin raise the flag. ESA says it plainly, the craft will loiter in a halo orbit until a target with a reachable energy budget appears, then depart as a composite and split for the fly-through. The JAXA page says the same with a different accent: multi-probe, multi-point, hydrogen imager, plasma measurements, close imagery. It is a repertoire, not a single instrument that turns a faint glow into a physical world you can reason about. Rubin's role in this choreography is to sound the alarm fast enough and cleanly enough that flight dynamics has options. That is why so much ink has been spilled on trailing and linking interstellar movers, smear their light across detector pixels. Naive software misses them. The conservatively phrased forecasts speak of a handful of interstellar alerts per Rubin year. The bullish ones speak of dozens. Either way, a steady trickle of candidates plus a craft at L2 is the difference between we took spectra for a few weeks and we flew through the wake and measured. Put it this way with 3. Hubble gave us the teardrop morphology of a living coma. Webb gave us the carbon dioxide heavy recipe. Mars, side orbiters, gave us a second balcony when Earth blinked. Rubin will make those alerts routine. And Comet Interceptor is the handshake we have been missing, the moment when dust fields, gas and surface are tied together in one pass. None of this makes 3i less strange, it makes the strangeness testable. So, we have the bell and we have the hand. In the next part, I'd like to ask the slightly braver question that follows: if the handshake goes well, could we ever bring a piece back? Not just microns of interstellar dust as Stardust once did, but a gram-scale sample from a truly alien nucleus. And what would it take in propulsion, shielding and patience to catch hold and return something that has drifted under another sun? Could we ever take a piece of a wanderer like 3i/ATLAS and bring it home gently, cleanly, without fooling ourselves? I think it's fair to say we've done the first rung already. 2 decades ago, Stardust flew through a comet's wake, caught grains in low-density aerogel, sealed them in a capsule and dropped them over Utah for careful years-long laboratory work. It even collected a sprinkling of interstellar dust on a separate tray while it cruised. That's not romance, that's the mission profile as NASA wrote it down. A hand-wavy but honest sketch of how that worked goes like this. The spacecraft threaded the coma of Comet Wild, 2 at roughly 6 kilometers per second, and a silica aerogel panel, think of it as a solid smoke, let dust burrow to a halt along carrot-shaped tracks, minimizing shock. The grains changed, of course. High-speed capture always leaves a fingerprint, but a great deal of structure and chemistry survived. Years later, the little cone-shaped capsule came scudding back through the air at more than 12 kilometers per second before parachutes and helicopters finished the story. That combination hypervelocity catch, then Earth return, is a proven path for solids. However, if the goal is not just dust, but ice and gas as they exist inside an active comet, the engineering gets harder. Volatiles don't tolerate being slammed into aerogel at several kilometers per second. They flash off and the chemistry rewrites itself. That is why the CAES-AR mission concept, Comet Astrobiology Exploration Sample Return, was so interesting. It proposed to land acquire tens of grams of material from 67P Churyumov-Gerasimenko, and then separately trap the released gases in a dedicated reservoir, preserving the evolved volatiles rather than letting them vanish, while keeping the solid sample as pristine as possible on the journey home. In their technical notes, the team put it plainly: this retains much of the science of a true cryogenic return, without the mass and risk of hauling a deep freeze across interplanetary space. It's a beautifully dull solution to a hard problem. So you can imagine 3 tiers of ambition. Tier 1 is Stardust style, a fast fly-through that catches dust from an interstellar visitor, feasible, affordable, and honest about the fact that ices won't survive impact. Tier 2 is CAES-AR style rendezvous, with a pristine long-period comet discovered early enough, sampled gently, and return solids, plus a bottle of the gases that boiled off your chemistry book intact down to the small print. Tier 3 would be the dream rendezvous, with an interstellar object, match its speed, touch, take, and come home cold. That last step isn't forbidden by physics, but it sits beyond what we can do quickly. The trouble is velocity. Interstellar visitors carry a hyperbolic excess of tens of kilometers per second. To match them, you need either exquisitely timed gravity assists and a scorching, sun-skimming burn, the so-called Oberth trick, or revolutionary propulsion. The Project Lyra studies sketch just such chase trajectories to Oumuamua, and concluded that while an intercept might be squeezed from present hardware with extreme architectures, a rendezvous, let alone a sample return, stretches the envelope. On the other hand, a fly-through that samples dust from an interstellar visitor is within reach today. We know how to do aerogel capture, we know how to build a stout, clean capsule, we know how to curate micrometer, scale grains for years in nitrogen cabinets. If you ask me for a conservative near-term path to alien solids on the bench, that's it, pre-position. A small, quick launch craft with a collector let the survey telescopes raise the flag, then sprint for a dusting. It won't give you intact ices, but it will give you the mineralogy and a residue of organics written in the grains themselves, enough to test whether the dust that glues worlds together is universal in composition or speaks in regional dialects. And because the collector is passive, the risk stays modest. If instead we target an ordinary but pristine long-period comet for a full sample return, then CAESAR's engineering playbook is waiting. Keep the solids clean, capture the volatiles in a separate sealed reservoir, and manage the thermal history so you don't rewrite the chemistry on the way home. That approach was laid out in the NASA technical studies in some detail: what to trap, how to bottle it, and how to track temperature and pressure from scoop to curation. The beauty here is that once the volatiles are isolated in their own gas bottle, you can read them like a diary without guessing what escaped during the cruise. Whatever the tier, there's a quiet framework: we must respect planetary protection. In practice, that means containment on the way down, curation in controlled facilities, and crucially, a plan for what you do if the container is even hypothetically compromised. The COSPAR policy is unambiguous: missions that might bring unsterilized material from potentially habitable environments fall under restricted Earth return, and if secure containment is in doubt, the sample must not come back. NASA's own pages make the same point in plainer words: protect other worlds from us, and protect Earth from what we bring home. The aim always is curiosity with care. Where does Comet Interceptor fit in this ladder? It is not a sample returner by design. It is a multi-probe flyby, built to turn paradox into measurement. 3 vantage points, 10 instruments, dust counters, plasma suites, near-infrared and visible images, and a wide-field coma mapper. In other words, it gives us the context: jet, geometry, grain sizes, gas mix field draping that would make any future sample 10 times more valuable because we'd know what part of the story it came from. Think of it as reconnaissance for our eventual ambitions. Put it this way: a gram of interstellar nucleus brought cold to Earth would change a field. But the path to that gram is incremental dust first, gases next, rendezvous later, and the discipline is to keep each rung justified by what the last one taught. Along the way, we will learn the practical things: how fast a collector can safely fly and still keep organics readable, how to bottle carbon dioxide-rich vapors without loss, how to certify a container to restricted Earth return standards so that curiosity never outruns caution. None of that is glamorous. All of it is the scaffolding under a moment that one day will look simple. Someone opens a vial in a clean room, bright as snow, and the first intact ices from another sun begin to sublimate into our instruments. So, the honest answer is yes, pieces can come home, but they will come in steps, and the first steps are dust and gas caught with patience rather than heroics. In the next part, I'd like to set the engineering on the bench beside the human scale, what it means to be a small, warm species that can read the mail of other suns, how we carry our wonder without hype, and why a faint carbon dioxide-rich traveller like 3I/ATLAS can make a long night feel a little larger and somehow kinder. Now, the human turn. I think it's fair to say that 3I/ATLAS offers 2 kinds of astonishment at once. There is the technical astonishment, the business with hyperbolas, spectra, dust fans that seem to point the wrong way until geometry taps you on the shoulder. And there is the quiet astonishment that on a small warm world under a sky we've stared at since there were campfires, we can read the mail of other suns. I like that image because it keeps the scale right. We are not conquering anything, we are opening a letter and trying not to smudge the ink. Put it this way: when I was a student, an interstellar visitor was a line in a textbook and a wistful maybe. And now, with scarcely a decade between them, we have 3 of them on the ledger: a shard that behaved like a splinter, a classic gassy traveller from a colder pantry, and now a carbon dioxide forward comet that teaches a lesson in projection. If the Vera C. Rubin Observatory does what it promises, those may become dozens. The rhythm changes from an isolated gasp to a steady breathing in. And that matters because wonder, to stay honest, needs repetition. One extraordinary object invites a story. a population demands an explanation. There is an ethical rhythm here as well. We owe it to one another to say what we know, how we know it, what we don't know, and how we mean to find out. That 4 beat keeps the temperature down and the doors open. With 3i, the beats are clear enough. We know it is interstellar because the orbit is hyperbolic and cannot be made bound by any plausible gravitational trickery close to home. We know it is active because telescopes as different as Hubble in Earth orbit and large ground-based mirrors on mountain tops have seen the teardrop glow and measured its growth. We don't yet know the nucleus size or spin with confidence. The coma hides the core and the geometry has been awkward. And we will find out by doing the dull, beautiful things, gathering more precise positions to sense the tiny, non-gravitational push of uneven outgassing, revisiting the colors and polarization of the dust as the viewing angle changes, returning to the spectrum as sunlight warms deeper layers of ice. I like too that our institutions have learned a kind of bedside manner. The Minor Planet Center keeps the bookkeeping clean. The wide field surveys give us the timestamps and the first orbits. Space agencies write public pages that begin with distances and dates rather than with adjectives. And the International Asteroid Warning Network corrals 1,000 small telescopes into something like a single instrument by aligning methods and calibrations. It is not glamorous to standardize apertures and centroids for fuzzy fast movers, but that is precisely how a headline becomes a measurement. The quiet heroism is paperwork and patience. From the human side, there is another responsibility. We rarely name out loud tone. It is tempting when a feature looks uncanny to reach for the Baroque explanation first. But the universe is generous enough that you almost never need to. The sunward fan that prompted talk of strangeness dissolves under a second vantage and a week of geometry into ordinary dust, launched gently from a sun-facing patch. The lesson is not that we should be dull. It is that a calm story told well is more beautiful than a thrilling story told quickly. If you keep returning to the photons, the counted, calibrated photons wonder has a way of deepening, not shrinking. And then there's us here listening. 3i does a small kind thing for the spirit. It says without fanfare that our kitchen is not the only one. Our planet-making recipe is not unique. There are colder pantries and warmer ones. There are disks that trap volatiles differently. There are grains that glue themselves into pebbles under skies with more or less ultraviolet or with different traffic of migrating planets. That could be intimidating if you wished our story to be singular. I find it comforting. In some sense, the more kitchens there are, the more likely it is that meaning, whatever that is in a cosmos of suns, arises often enough to matter. The numbers do the quiet poetry, a galaxy of hundreds of billions of stars, each with a chance to cook dust into ice and ice into worlds, each a candidate for letters like this. You might ask, and it's a good question, whether any of this touches life in a way that is more than metaphor. I'd say the answer lives at 2 levels. At the speculative end, there is the old banner of panspermia molecules, and in the long shot, microbes travelling between stars. The careful version is mundane and testable. We know complex organics form in cold interstellar clouds. We know comets and carbonaceous rocks deliver those molecules to young planets. We know that hardy organisms on Earth can survive for years in space if you shield them. Whether they can cross millions of years of interstellar cold is doubtful without extraordinary protection, but that is not where the main interest sits. The main interest is in chemistry, whether the pantry of prebiotic molecules is universal or speaks in dialects. 3, as carbon dioxide-led activity tells us where to look, which drawers to open first, when we finally fly through the wake of a visitor with mass spectrometers that can sniff fragile compounds. It is a practical romance poetry tied to a checklist. There is also the civic level close to home. Objects like 3i are not threats in any ordinary sense. They are far and faint. But the same eyes that find them also find the nearer, duller rocks that sometimes matter to us in a more immediate way. When people ask why surveys and networks and data standards deserve their slice of the public purse, 3i offers a gentle answer. The system that can calmly spot a fleck from another sun is the system that can calmly spot the thing that will pass a little too close to ours. The disciplines are the same: wide eyes, fast alerts, shared methods, patient follow-up, beauty and safety for once point in the same direction. I don't think it's an overreach to say that this work changes the texture of a night. You step outside, you let your pupils widen, and you know that somewhere in that darkness a small ancient body is sifting sunlight into a stream of carbon dioxide and dust that remembers another nursery. You know that part of that stream is bent by the breath of our star into a shape that a poet might call a fan and a physicist might call a projection. You know that an instrument a world away is catching those photons and another from a second balcony is catching them again at a slant, and that between them a story is being told that did not exist when you were born. That's enough most nights. So, if 3I/ATLAS brings us anything beyond data, it is a posture, quieter voices, steadier hands, a willingness to let numbers carry the oar. In the next part, I'd like to bring that posture to the obvious forward question, what could surprise us next, and walk through a few honest possibilities, a visitor that fragments and bears its core, a faint interloper found so early that an intercept becomes possible, or a chemically warm comet that wakes late and forces us to rethink our selection biases. In the end, I think it's fair to say we have walked with a small traveller for long enough to let it go. 3I/ATLAS came to us on a curve that does not close, carrying a chemistry that remembers a kitchen not our own, and a lesson in perspective written as a sunward fan that turned under a second balcony into geometry. In some sense, that's the whole story, a faint fleck, a handful of careful measurements, and a wider sky than we began with. Now, before we lower the lights, I'd like to leave you with the simplest picture I know. Imagine the solar system as a quiet harbour at dusk. Far out of tide, you cannot feel lifts and lowers a long chain of comets. Now and then one slips in drawing a soft line through the air with dust and cold gas. Rarer still, something arrives that does not belong a visitor from the wider sea. Its course bent slightly by our star, its wake briefly lit by our sunlight and then gone. We watch, we measure, and we write a little note in the ledger. That's all, and it is enough. Put it this way, the marvel is not that we can turn photons into molecules and motions, though that is a marvel. It's that we can do it gently. We can say with steady voices, this is what we know. This is how we know it. Here is what we do not yet know, and here is how we mean to find out. We can enjoy the poetry of a carbon dioxide wind leaving an ancient surface, while keeping our feet on the numbers that make the poetry honest. We can let a small, quiet fact do the heavy lifting that somewhere else under another stardust and ice learned the same tricks they learned here. I like to remember too that we didn't go looking for mythology, we went looking for measurements. The Minor Planet Center did the dull heroism of bookkeeping. Wide field cameras swept and linked, telescopes on mountains and in orbit took turns across the spectrum. Spacecraft at Mars watched when we blinked. Soon a survey in Chile will make such alerts routine, and a patient craft at the Sun-Earth L2 point will wait to offer a hand when the next true stranger wanders close enough to greet. There's comfort in that choreography. It says we can organize our curiosity into something like grace. And if you ask what we carry away, I'd say it is not certainty but scale. The Milky Way is a garden of kitchens, from cold pantries rich in carbon monoxide to warmer rooms where water drives the steam. Our first 3 visitors happen to sample that variety. Another dozen will sample it better, another few dozen better still. In a handful of years, we'll be able to say with numbers rather than adjectives whether comets like ours are typical or whether our recipe is a regional dialect in a broader galactic conversation. That is a good ending for a small species, more honest questions than we began with, and a clearer way to ask them. There is tucked beneath the technique a human rhythm I find calming. We began with a hook. Could this be the key to something deeper? We added a handrail of history. We met a paradox and dissolved it with 2 frames. And we arrived at the quiet, ethical turn that if we are reading other suns' mail, then we should do it with care. Care with language, care with numbers, care with how we share uncertainty. Not because the cosmos demands etiquette, but because we do if we're to keep the wonder intact. From the edge of science to the edge of self, the lesson feels the same. You think of a speck moving wrongly enough that yesterday's bookkeeping will not do. You think of a team who notices and a community who gives that noticing a shape. You think of a sky where the ordinary refuses to stay ordinary under a better look. And you think of a world ours where people will step outside tonight, let their eyes adjust and know that somewhere beyond the bright planets, a visitor from a different nursery is quietly unspooling its history into light. That thought has a way of smoothing the corners of a day. If I were to leave you with one last image, it would be this. Picture a page in a long, careful index. On it 3 lines, 1I/Oumuamua, 2I/Borisov, 3I/ATLAS. Next to each, a short note in a small hand shard. Classic comet. Carbon dioxide forward. In the margin, faint pencil marks, dates, distances, a few cautious arrows. In time, the page will fill, then we'll turn to the next. We are not writing scripture, we are keeping a diary. And one day someone will look back over those pages and see not a handful of wonders, but a pattern, the way the river flows, the flavours of its spray, the common physics that binds a galaxy of kitchens into a single legible universe. So let the comet go. Let it fade back into the dark that made it. We'll be here when the bell rings again. Quiet instruments, ready patient hands at the controls, and the same small promise on our lips to turn light into meaning as gently and as honestly as we can. And if for a moment the night feels larger and kinder for that promise, then I think it's reasonable to say we've understood what 3i came to teach.